Okay, guys, our lesson today is to be able to, recognize linear and nonlinear functions, using tables and using graphs. The graph of a linear function shows a constant rate of change. A nonlinear function does not have a constant rate of change, so its graph is not a line. And remember, another term for constant rate of change is slope. All right? So, in a previous lesson, we've learned that linear functions have graphs that are straight lines. This is because the rate of change between any two data points is constant. Nonlinear functions are functions whose rate of change are not constant. All right, so if we take a look at some examples here, we're given two tables. All right, and we want to determine if the tables show linear functions or nonlinear functions. All right, determine whether each table represents a linear or nonlinear function and explain. And if you look at this first example here, the rate of change is constant. If you look at your rate of change in your y values, right, there's a constant decrease of 15. If you look at your change in your x values, there's a constant increase of 2. Right? And we know that your rate of change, right, is your m. That's your change in y ratio, right, over change in x, right? Your change in y over change in x. It's a ratio. And we would look at that as negative 15 over 2. It's constant. And whereas if you look at example 2, notice the change in y values. We go from 1 to 16, that's an increase of 15, but then we go from 16 to 49, that's an increase of 33, then we go from 49 to 100, right, and that's an increase of 51, right? The rate of change is not constant. As x increases by 3, y increases by a greater amount each time. The rate of change is not a constant, so this is not, right, a linear function. It is a non-linear function. And if we drew, right, connected our points here, you would see, right, we have a curve. All right. Okay. Well, we have two examples here, right? Let's look for that rate of change and be able to identify which table represents a linear function and which table represents a nonlinear function. All right. So let's take a look. Let's start with our change in y, right? That's a decrease of 4, decrease of 4, and a decrease of 4. Our change in x, increase of 5, increase of 5, and increase of 5. So we see that our rate of change is constant, right? So that's a linear function, right? Linear functions have rates of change that are constant. And if we look at example B, change in y, increase of 2, then we have an increase of 6, then we have an increase of 10, right? That rate of change is not constant, even though the change in x is constant, right? Increase of 2, increase of 2, increase of 2, that rate of change in the y values is not constant. So this would be an example of a non-linear function. So we're looking for that constant rate of change, right? Constant rate of change, it's a linear function. All right. Next page. Use the table to determine whether the minimum number of calories a tiger cub should eat is a linear function of his age in weeks. Use the table to find the rate of change. All right. So if we take a look at our table, right, we see a change of what here? From 825 to 1,000, that's an increase of what? 175. Right, so that's 175 there. Then we have an increase of 185 here. Here we have an increase of what? 135 maybe, right? Don't hold me to my math, but I think I'm doing that right. And here we have an increase of what? 100. Right? So even though the age in weeks, right, that's a constant increase of 1, right, the rate of change, right, is not constant, right? We see that. So this would be nonlinear, right? And it's nonlinear because of rate of change is not constant, right? It's nonlinear. The rate of change is not constant. Is not constant. All right. Let's take a look at our next example, right? We just want to be able to identify that rate of change. Problem says tickets to the school dance cost $5 per student. Are the ticket sales a linear function of the number of tickets sold? And explain, right? So let's look for that rate of change. Increase of 5. Increase of 5 here. When we look at the number of ticket sales and the cost, you have an increase of 1. Increase of 1, right? And we see that the rate of change is constant, right? The rate of change is constant. And when that rate of change is constant, right, it's a linear function. And that's what we do when we're identifying the functions from tables. We're just simply looking for that constant rate of change. A constant rate of change means that the function is linear. If there is not a constant rate of change, it is nonlinear. All right, may still be a function, but just nonlinear. Okay, our next example. A square has a side length of s inches. The area of the square is a function of the side length. Does this situation represent a linear or nonlinear function, and explain? Make a table to show the area of the square for the side lengths of 1, 2, 3, 4, and 5 inches. And that's what we see here. Here's our table, right? And the top row of our table represents the side lengths of 1, 2, 3, 4, and 5 inches. Well, what are the corresponding areas? When the side length is 1, the area is 1 inch. When the side length is 2, area is 4. When the side length is 3, the area is 9. When the side length is 4, area is 16. And when the side length is 5, the area is 25. Right? But let's look for that rate of change. Increase of 3, increase of 5, increase of 7, and an increase of, what do we got? Increase of 9. Right? The rate of change, right, even though these are increases of 1, right, the rate of change is not constant. Right? And because that rate of change is not constant, right, we know that this is going to be non-linear, right, because that rate of change is not constant. Okay, next slide. Well, you should probably try these on your own. You'll give it a shot, see if you can identify them correctly. All right, and give you a chance to try that on your own, and then we'll go through it. All right. Let's check and see. Linear or nonlinear? Let's look at the rate of change here. From 40 to 32, that's a decrease of 8. Decrease of 8 from 32 to 24. And from 24 to 16, that's a decrease of 8. This is increase of 3, increase of 3, increase of 3. Right? So this is linear. Right? And our explanation, because they do ask us to explain here, the explanation, the rate of change is constant. The rate of change is constant. Constant. And when we look at the second example, right, let's look at our change in y values here. From 2 to 11, that's an increase of 9. 11 to 33, that's an increase of what, 22? 33 to 88, that's an increase of what, 55? All right, increase of 2 in our x values, right? But we can see very clearly this would have to be nonlinear, and it's nonlinear because the rate of change is not constant, right? And it's that simple. Right? When we're looking at tables, we just have to identify that rate of change. Right? A constant rate of change describes a quantity that changes by equal amounts over equal intervals. Right? We see that over the same intervals of 3, the rate of change is constant in example A. Whereas in the same interval, example B, the rate of change is not constant. All right, let's see what we got next. All right, now, when we're identifying functions from graph, linear functions, it's the eye test, essentially. Right, do we see a straight line that's not vertical or not? All right, and in example A, right, this would be nonlinear. Right, and it's nonlinear because, right, the graph is not a straight line. Right, so this would be a nonlinear function. Right, and what's our explanation? Our explanation is the graph is not a straight line. Graph is not a straight line. Right, a straight line that's non-vertical. Example B, right, we do see a straight line, so this would be an example of a linear function. Right, it really is as simple as the eye test. If we see a straight line that is, not vertical, it's a linear function. Right, so our explanation, it's a linear function. The graph is a straight line. It is a straight line. All right, let's see what we got here. We continue. So now we have some examples down here, right? We have tables, we have some graphs. Are they linear or nonlinear? All right. If we look at this first table, let's look at our change in y. Decrease of 5, decrease of 5, decrease of 5 over the same interval of 7. So this would be linear function. Right, and it's a linear function because the rate of change is constant. Right? Example 2, decrease of 4, decrease of 4, decrease of 4. Let's see, what's the interval here? 2, 2, increase of 2. This would also be a linear function. Right, and they're linear functions because the rate of change is constant. We look at example 3, right? This is nonlinear. Right, and it's nonlinear because the graph is not a straight line. Right, it's a V shape, and you guys are going to learn that's an absolute value function when we see those V shapes. All right. Example 3, identifying nonlinear functions with equations. Well, let's see. Is there somewhere where we have that information, right? If we're talking about an equation, and right, we do not. All right, so when we talk about linear functions, let me go back here, and we want to identify linear functions with equations, right? We're looking for one of two things, right? What's that thing going to look like on a graph? So we're looking for the form y equals mx plus b, right? That's what we're looking for. Y is equal to mx plus b, right? We know that y is equal to 4.7, right? This is going to be linear, right? Because that's going to be a horizontal line, right? Through 4.7 on the y-axis. We know y is equal to pi times x, right? That is an equation in slope-intercept form as well, because the slope here would be 3.14. It's going to be pi. Example D we know is linear, right? Because if we actually use the distributive property, y is going to be equal to 4x minus 4, so we know that that is linear as well. So example C is the nonlinear function, right? We cannot have that x dividing 4, because that's going to give us, if we graph it, right, that would give us an example of a nonlinear function, right? What would that look like if we graphed it? Well, do a column for x and a column for y, just so we could see it. So let's do 0, 1, 2, 3. And when x is 0, we know it's what? Undefined. Because we can't divide by 0, undefined. And when x is 1, we get what? That's going to be 4. When x is 2, it's going to be what? 2. And when x is, let's do 4, right? Because that'll go in evenly. Right, 4 divided by 4 is 1. And if we are graphing that, let's see if I can bring up some graph paper here and graph that so we can see it. Where's my graph essentials? Nope. I want my content. I need my themes. All right, and if we were graphing that real quick, let's do that. All right, if we're graphing those ordered pairs, let's see what we got. We can't have a point at 0 because it's undefined. We have 1 comma 4. We have 2 comma 2. And then we have 4 and 1. Right? And we see, right, there's curve there, right? It's not straight. Right? That's curve. Right? Let me undo that and try to use a straight line. Right? I can't connect those points, right, with a straight line. Can't do it. Right? Can't do it. Can't connect those points with a straight line. So that is a non-linear function. For example, problem 3. All right, so we continue. All right, our next example. Account A earns simple interest. Account B earns compound interest. The table shows the balance for 5 years. Graph the data and compare the graphs. All right, so here's what we're looking at. Account A, account B. Right, if we're looking at our differences here over the same interval, here's our interval, over 1, 2, 3, 4, and 5 years, account A, we see a constant increase, right? $10, increase of 10, increase of 10, increase of 10, increase of 10. And if we look at the graph for account A, right, that blue line there, it's a straight line, right? So that's a linear function. And we see it's linear because our rate of change is constant. If we look at example B, or account B, I'll do that in red. Increase of 10, increase of 11. This is what? Increase of $12.10. Here we have an increase of what? $13.31. Here we have an increase of what? $14.64. Right, needless to say, that rate of change is not constant. And if we see account B here, right, shown with the red line here, right, it is a curved function, so that would be nonlinear. And that's what we see here, right? It says both graphs show that the balances are positive and increasing. The balance of account A has a constant rate of change of 10, so the function represents the balance. So the function representing the balance of account A is linear. The balance of account B increases by different amounts each year because the rate of change is not constant. The function representing the balance of account B is non-linear. All right? We continue. All right? So if we look at these equations here, right, if we want it as a linear function, we have to see that form y is equal to mx plus b, right? That's what we're looking for. Right? We see it here. Example 4, y is equal to x plus 5. See our y-intercept is 5, slope's 1. We know that's a linear function. Right? If I look at problem 3, right, y is equal to 4/3 x. What's the y-intercept here? 0. What's the slope? 4/3. That's a linear function. All right? But problem 5, what do we see here? We see an exponent. And in order for a function to be linear, the power of x has to be 1. The variable x has to be to the first power. Here our variable is to the second power, so this would be nonlinear. For problem 6. Question 7, or the got it problem. A square has side lengths of s inches. The perimeter of the square is a function of the side length. Does this situation represent a linear or nonlinear function? Well, let's think about that for a second. Right? If we have a square, right, whose side is s. The perimeter of the square would be s plus s plus s plus s. Or another way of writing that would be the following. The perimeter is equal to 4 times s, right? And if you look carefully, that is in the form of y is equal to mx plus b, right? Where s is your variable x, m, your slope would be 4, y-intercept would be 0. So this would be, right? This would be linear, right? That's linear, right? Linear function. All right. Now we have some guided practice problems here, right, that we can work on, right? Just a couple, good practice for you guys. You can look at those tables and try them on your own. See if you can identify if they're linear or non-linear. All right. Okay, let's take a look at this first one. Increase of 2, increase of 3, increase of 4. Rate of change is not constant over the same interval of 1. Right, so that's nonlinear. If we look at our second example, negative 3 to 9, what's that? That's an increase of 12. Right, 9 to 21, that's an increase of 12. 21 to 33, that's an increase of 12. Over the same interval, right? That's what? 3, 3, and 3. So this, of course, would be a linear function because the rate of change is constant. All right. Problem 3. The table shows the measures of the sides of several rectangles. Are the widths of the rectangles a linear function of the lengths? Well, our lengths are in the top row, our widths are in the bottom row. Let's see what we have here. We have a difference of 48, difference of 8, difference of what? 1.6 over the same interval. What's that? Interval of 3, interval of 4, interval of 6. All right, is 48 over 3 the same as 8 over 4? No, right, because negative 8 over 4 is negative 2. Negative 48 over 3 is, what's that, negative 16. So this would be nonlinear. It's nonlinear because the rate of change is not constant. Rate of change is not constant. All right. Then our last one here. Let's see. What does it say? It says a cube has a side length of s meters. The volume of the cube is represented by the expression s cubed. The volume of the cube is a function of the side length. Does the situation represent a linear or nonlinear function? And explain. Right? Well, what are we talking about here? The volume of a cube. Right? Here's our cube. Right? Something like that. Not the best cube I've ever drawn. Right? Where the side length is s. The volume is equal to the length of the side cubed, because it would be s times s times s. And because we see the exponent here, right, if we see an exponent in the function, it cannot be linear. So this is nonlinear. And it's nonlinear because the variable is raised, right, because, right, s is raised, right, to a power other than 1. To a power other than 1. Other than 1. All right, so just to review, when we're trying to identify functions through graphs, linear functions, the graphs will be straight lines. Nonlinear functions, the graphs will not be straight lines, right? But when they're linear, they have to be straight lines that are non-vertical straight lines, right? That's important. And then when we're looking at identifying functions from tables, we have to see that rate of change. It has to be constant. If we see that constant rate of change, we have a linear function. When that rate of change is not constant, it's a nonlinear function. And lastly, when we're looking, identifying functions in equation form, we have to be able to see the equation in the form y equals mx plus b, because y equals mx plus b is the equation of a straight line. So if we see, if we cannot write that equation in the form of y is equal to mx plus b, it's a nonlinear function. And if we see an exponent of the variable other than the power of 1, nonlinear function. All right. Well, I hope that's been helpful, and we'll see you soon.